introduction. Today, I will introduce to the University of Tokyo the recent achievement of realizing world's first deep space micro spacecraft, PROCYON. This mission goes to deep space, and this was a big challenge for small satellites. So I will talk about how we achieved this big challenge, and I would like to look back my experience from CANSAT to CubeSat to the realization of this spacecraft. Well, this is outline of my talk. First, I will introduce you to my personal experience on nano or micro or small satellites. This includes from CANSAT and CubeSat to a larger mission conducted by a space agency. And then I will talk about PROCYON, focusing on the mission and the spacecraft design and achievement. I will also discuss future perspective of deep space mission by small satellites. And finally, as a conclusion, I will give some concluding remarks. Okay, this slide shows my personal experience on small satellites at the University of Tokyo and the Japanese Space Agency, JAXA. When I was a student at the University of Tokyo, I was involved in the development and launch of one CANSAT and two CubeSats, which includes the world's first CubeSat in 2003. And after graduating from this university, I moved to JAXA, and I was involved in the development and launch of the world's first solar sail named Icarus. Then I returned to University of Tokyo as a professor in 2012 and started the PROCYON project. It became the world's first interplanetary micro spacecraft. So now let me introduce each satellite project and what I experienced. And much like most of you, the starting point of my satellite development experience was CANSAT project. CANSAT is a GeoScan-sized satellite model, and many universities around the world are using this CANSAT as for student training. And these photos were from when I launched my first CANSAT in the US about 13 years ago. What I learned from CANSAT project were like this. The first was the fundamental of making things such as electric circuit and the mechanical structures and so on. And I also learned the difficulty of project management even in a very small team. And this time, our mission was to fly a CANSAT by autonomous control by using a parafoil, and but the mission was not successful. So I learned the difficulty of making mission success at one-shot launch opportunity. But this is the most essential part in space missions, so I think the CANSAT project can offer very practical space engineering education. And the next one was the CubeSat project. We developed and launched two CubeSats in 2003 and 2005. And the first one, named Psi-4, achieved the world's first successful launch and operation of CubeSat. And this is our second CubeSat, Psi-5, which conducted a mission to demonstrate radiation tolerant to new solar cell in space. What I learned from these two CubeSat projects was first is how to make very small satellite with commercial, high performance, but not space qualified electric parts. And the second is how to make the satellite survive in space environment. This is very important. What we did was not just applying redundant, simple standby redundancy system, but we applied functional redundancy and cross-check redundancy against the malfunctions caused by a wide variety of space environments. This strategy does not require much additional resources for the satellite, so this way, this was a key to realizing very low-cost satellite development while maintaining reasonable reliability of the satellite. So thanks to this strategy, both two CubeSats are still operational in orbit over 10 years in space. And after graduating from the University of Tokyo in 2007, I started to work for JAXA, and I was involved in the development and the launch of the world's first solar sail named Icarus. Icarus was a 300 kilogram interplanetary spacecraft, and this class of spacecraft is much larger than our CANSAT or CubeSat. So I learned a lot of things from this project. The way how a National Space Agency assures reliability of in a large mission was rather conservative. And it was quite different from my familiar CubeSat ways of mission assurance. But I understood that the way is certainly logical and valid for this class of mission. So it's not a surprise that the way is certainly the optimal way of assuring mission success depends on the size and cost of the spacecraft. So expensive mission should take a more conservative way, and low-cost mission can take risks. And I also learned how to make a spacecraft to operate in deep space. It was certainly different from our Earth-orbiting satellite, and I had thought it was a very difficult thing, but I found that it was not too difficult. So I started to think that the deep, small satellite might go to deep space and can conduct some challenging mission. So when I returned to University of Tokyo as a professor in 2012, I believed that the deep space should be the next frontier for small satellites. It was very fortunate for us that piggyback interplanetary launch opportunity together with Japanese Astro Sample Return Mission Hayabusa 2 was announced in 2013. So our laboratory and JAXA jointly proposed interplanetary micro satellite mission PROCYON, and they started the development. Since anyone has never realized such a small interplanetary spacecraft, we defined PROCYON's primary mission as a demonstration of micro spacecraft bus system for deep space exploration. Which is to show that the spacecraft of this class can conduct some deep space mission by itself. After the launch into interplanetary trajectory by the rocket, we will conduct this mission for several months. The mission includes the power generation and management in deep space, and thermal design to accommodate a wide range of solar distance and a wide range of power consumption mode. And we also need 3-axis attitude control with very high stability. And in deep space mission, we should have special communication and navigation technology with high efficiency, high output, and precise navigation. And we also need a propulsion system in deep space mission. So we demonstrate a micro propulsion system in this mission. We have a reaction control system for attitude control and momentum management, and we also have ion propulsion system for trajectory control. And after completing the primary mission, we will conduct these engineering mission and scientific mission as a secondary mission. Secondary mission means optional or advanced mission. For engineering mission, we have deep space maneuver to perform Earth swing-by and the trajectory change to target an asteroid flyby. And after that, high-resolution observation of asteroid during close and fast flyby is planned. And optical navigation and guidance to an asteroid is conducted by using a special telescope, and this telescope also performs automatic tracking observation of an asteroid during close flyby. And for scientific mission, we plan wide view observation of geocorona from the outside of the Earth's atmosphere. And we designed and developed the spacecraft to achieve such primary mission and secondary missions. And this is the external view of PROCYON. It has 4 solar array panels to be deployed like the left figure. And we have a special telescope at the bottom of the spacecraft. When the spacecraft passes by the asteroid moves like from this blue line. And this telescope can rotate around the red axis, and they can control the line of sight and track the asteroid direction during flyby, while the spacecraft can maintain 3 axis attitude stabilization. The intended flyby altitude is as close as about 10 to 30 kilometer, and the intended surface resolution is about 1 meter. And this is internal view of PROCYON. The size of PROCYON is about 55 centimeter, and you can find a lot of components really integrated into a this small structure. This is like a CANSAT or a CubeSat or something. And this is an actual photo of inside the spacecraft. And let me show you some pictures from our development phase. First, we built STM, a structure and thermal model, to verify our thermal design and structure design. And this is a photo from the STM test. And this slide shows how we are integrating the flight model at the University of Tokyo. This is a spacecraft and integration. And we conducted the end-to-end test of the ion thruster in a vacuum chamber like this. You can see the plume of the ion engine. Engine here. This is a plume of ion engine. Okay. And this is some vacuum test for the flight model. And this is a vibration test and a shock test. And finally, PROCYON was launched together with Hayabusa 2 by the H2A rocket in December last year. This is the main, the blue circle shows the main payload, Hayabusa 2, and the red circle shows PROCYON installed at the bottom of the spacecraft. And the primary mission was a demonstration of the bus system for deep space exploration, and it was quite successful. Power system was okay, and temperature control was okay, and 3-axis attitude control was okay, and deep space communication and navigation system was okay, and our propulsion system, including RCS and ion propulsion, worked well. So we demonstrated that the spacecraft system can, this class of spacecraft can conduct deep space mission by itself. And then part of the secondary mission was also successful. We succeeded in this scientific mission, geocorona observation outside the Earth's atmosphere, and we are preparing a paper to submit to a science journal. So I'm sorry I cannot show you the images today. And unfortunately, engineering missions are not fully successful. We studied the deep space maneuver for the Earth swing-by, and the ion propulsion system worked very well for over several hundred hours, but the operation of the thruster suddenly stopped due to a short circuit in the thruster. So currently we cannot complete Earth swing-by to change the trajectory to fly by an asteroid. So this is a summary of the operation results. Demonstration of the deep space bus system was success, and the scientific mission was also success. And we failed, but we failed in the long-time ion engine operation for deep space maneuver and the subsequent asteroid flyby mission due to the short circuit in the thruster. But anyway, we demonstrated that the capability of this class of spacecraft to conduct deep space mission by itself, and it can be a useful tool of deep space exploration. So in the last part of my presentation, I'd like to discuss the future perspective of PROCYON type small deep space missions. Possible missions by micro spacecraft will be like this. Well, one is a precursor mission for a larger mission, such as a human exploration or asteroid mining or something, is the best application. Or we can consider a small-scale mission for very focused science with very limited instruments. And for trajectory and launch options for to perform deep space mission by small spacecraft, it is very important not to miss any chance to go to deep space. By taking advantage of its very short development time, we can flexibly respond to a wide variety of launch opportunity in the world. So the best option will be the piggyback launch with direct Earth escape trajectory, and flexible target selection will be possible if we can perform Earth swing-by like PROCYON case. And or piggyback with a lunar mission to a lunar transfer orbit is also possible. We can escape Earth's gravity by lunar swing-by and additional very small delta V. So yes, this is the concluding remarks. From my experience, I believe that the CubeSat way of building satellites can open a new door of space exploration. The CubeSat way is to boldly and carefully at the same time introduce novel technology in space mission, and to take risks and do some kind of the first thing challenging mission. And the rapid mission cycles will create innovation, I think. This is the final goal. And I think CanSat or CubeSat is the best first step toward this goal. So I would like to explore our own original frontier, and I want to make a new world of space exploration. Yes, thank you very much.